So we continue on our journey to understanding how the M-class CPUs boot up. So we are, as part of this video, uh, going to understand the boot up process. Now, my claim is before we try and understand the boot up process, there is a fundamental concept of interrupt handling that we would kind of need to take a look at and be thorough with it. And this kind of, how the interrupt handling or exception handling, this is also called exception handling. So how this concept ties into the boot process of the CPU, that becomes evident in a while as we go on to exploring this. And then, let's kind of dive in. So what we discussed in earlier videos was we have this we have the NVIC here, and we have the CPU, and this is the M-class CPU. And what happens is there are lines on the NVIC wherein you can have, let's say, a button, right? And you can press the button and generate an interrupt and so on and so forth. Well, this circuit might look something like so, and again, all of this is something like so. This is the controller, right? STM or something like that. But this is the CPU, and the CPU has NVIC connected to it, and so on and so forth. So now, when you press this button, let's say interrupt 25 occurs. And what we talked about is in normal situation, the CPU is executing the code, going about doing its normal operation. And then at this point in time, time is going downwards here. So as a result of, this event here, let's say the 25th interrupt occurs, the CPU kind of parks, so to speak, whatever it was doing currently, and then it goes on to executing something else, executes that, then comes gets done with this, then returns back here, remembers whatever it was doing earlier, and continues on. So now the thing is, we want to understand this process in a little bit more detail. Right. And understanding this, my claim is, will convince us or will give us hints as to how the CPU boots up. Okay. So we also talked about existence of R13, which was the stack pointer register, which pointed either to MSP or PSP. Then we had R14 and we had R15. So these are like the three registers that are of interest to us right now. So what it would mean for a processor to park the current process. This is, let's say, P1, so it was executing P1 and it needs to park P1 and go execute, let's say, some code which is labeled as ISR underscore 25. So it needs to kind of execute this code and then come back. So the question is that when the CPU is parking the current process P1, the two questions is, how does it park? And well, what does it mean to park? Right? What does it even mean to park a process? And park is a keyword that I'm using. You can think of saving the context. So this is also called saving the context. And what we are going to learn now will kind of, in the later videos towards the end of this course, come in very handy when we are talking about context switch of processes. Okay, so we want to explore what does it mean to park a process, or what does it mean to save the context of a process, and how does the CPU go about doing it? Okay, so we now have to return back to the programmer's model of the CPU. The idea is that everything that the current process is executing, or like the CPU, whatever it is doing relating to the current process, the state would be saved, or the state information is saved in the CPU registers, right? And now, if somehow all these registers, the values in these registers, and all is a stretch here, but if all these values can be saved somewhere in the memory, and if the CPU now decided to go execute some other code, then what it really means is that wherever the CPU, at whatever time the CPU wanted to park its state, so to speak, save the process, it will take the registers, internal registers somehow, and save it onto the memory somewhere. Where that somewhere is, we haven't talked about it. How the CPU goes about doing this, we also haven't talked about it. But think about this idea that if the current process was to be parked, so to speak, or the context of the CPU execution was to be saved, it would simply mean that the CPU registers, the values of those need to be saved elsewhere, because the values of the register are what conveys the current state of the CPU. And if we could save the current state, move the CPU to a new state. So, for example, if let's say, actually, let's talk about this in a little more detail. So, R15 is the program counter. So, wherever program counter is pointing to in the memory, that is the instruction that the CPU will fetch. So, if I could do something like this somehow, just somehow, and how that somehow works, we'll come to that. But if somehow I could take the CPU registers, put them on the memory, and change the program counter, let's say this is the program counter, change the program counter to point to this code, then essentially it'll start to fetch instructions from that location, which happens to be the procedure to handle the interrupt number 25. So it goes about doing its business, and then at the end here, if I could take all of these registers and load them back into the CPU somehow, right, all of these, then the program counter will be replaced with the value of program counter that was here, that was saved. And what that essentially means is the instruction that corresponding to P1 that the CPU was going to execute, well, the state of the system or the state of the CPU is restored back. CPU is pointing to this instruction right here, and then it goes about doing its merry business. Right? And this idea is absolutely key. The state of the CPU is represented by the registers. If somehow we take those registers, put them elsewhere, modify the value of those registers somehow such that the program counter points to the place where the code of interest is, in this case ISR underscore 25, then what happens is it will go ahead and start to fetch instructions from this location right here, the new location, and so to speak, all of a sudden the CPU is doing something else. Right. So we can kind of relate this to reading a book. So, and the reading the book example becomes more interesting in a bit. So let's say you were on, I don't know, page number 100, right? And then all of a sudden, someone gave you a call, this is the phone. So someone gave you a call and they asked you to read another book, right? And let's say you don't have a memory of your own for whatever reason. So you note down that you were reading X book, page number 100. Yeah, you note down whatever the line number and the para number, you take a note of it somewhere, and this somewhere is what I'm referring to, the memory. And then what you do is you move on to some page number and some book that the instructions you got on the phone, someone told you, and then you continue to read on. Let's say after a while you finish reading this book, then what you do is you come back, take a look at this memory here or page here, and then go back to book X, page number 100, line number so and so, and you continue on. So this phone call kind of in this very bizarre situation um, served as an interrupt. You reading another book, let's say, why was you switching the interrupt context? Well, actually, You saving the current state of your mind, so to speak, on a piece of paper, maybe. That is called parking your current process. And then you moved on to reading about why. After you finished that, you kind of came back to the piece of paper, figured what you were doing earlier, and went back to doing it. So hopefully this convinces you what parking the process or what effect an interrupt can have. Now, so we talked about the what does it mean to park the process. The what part, again, I'll just reiterate, it simply means take the CPU registers and very cleverly park them or save them on the memory. Where do we save it? How many of the registers we save it? All of that we are still to take a look at, and that brings us to the how part. So turns out that the M-class CPUs do the saving and restoring in hardware, right? In hardware, meaning they have the provision to on their own save the CPU registers and restore it back when an interrupt happens. And this kind of becomes a little more nuanced, and let's take a look at that. So we had 16 registers, right? We went from R0 to R15. So now what happens is, and we said R14, and then there is R13, and then there is R1, and so on and so forth. All of these registers, then there were some special registers, right? So now what happens is, whenever an interrupt happens, the CPU will go ahead and save some of the registers, not all, but some. So it will save some of the registers in the memory. And it will also figure out from where can it start to fetch the instructions to handle a given interrupt. And how does it fetch where to go and fetch the instructions from for a given interrupt handling? That also we'll figure out in a bit. But the idea is that it doesn't save all registers. It saves a certain set, a mandatory set of registers onto the memory. And which memory you ask? So it saves it on the stack. So the stack pointer here is used, so to speak, to save the information or save the registers. And this is very interesting. And what registers does it save? Well, I might be recalling this incorrectly, but what it does is, I think it something like so. I think 11 or so. It in total saves. I might be wrong here, but and I'll kind of add a note on this. And I think this is also a good question as to which registers it saves. But let me give you. So it will save the top 4 register, the R0 through R3, and I suppose it saves. I think it saves R14, R12, R11, and one more, R10 maybe, right? And this needs to be checked. But the idea is that it will save 8 registers, 4 from the top and other 4 from the bottom somewhere. Link register, program counter. I don't think it saves stack pointer, but R12, R11, something of that nature. And again, I'll clarify which register it saves as a note or something. But those registers go on to here. And the question about why doesn't it save the other register? Well, we'll come to that in a bit. But once it has saved this register and the hardware does it for us, the hardware knows that, hey, I have the stack pointer here. I'm going to use that location to save 8 registers. Fair? Then what it does is it automatically loads R15, and note that the R15 value is also saved. So when it's going to restore, the R15 value will be restored. That's a given. So now the thing is, where should the CPU go to handle the interrupt? And my claim is the R15 value automatically gets loaded, and the automatic also will come to that. But it automatically loads that and straight up jumps to that memory location. Jumping meaning it will start to fetch instructions from that memory location. And now the idea is, if the code here wanted to use the unsaved registers, if it wanted to use that register for its own purposes, before it uses that, it needs to save those registers on the stack. So then the idea is this, that when an interrupt happens, the CPU automatically saves 8 registers on the stack. Then there are some other registers which have the old value that the old process was using or using the registers for. And the claim is R15 all of a sudden points to the new location from where instructions are to be fetched. And if that piece of code or if that procedure wanted to use the unsaved registers, it must first save the value of that register on the stack. And also towards the end, when this procedure is kind of winding down, it must copy back that saved register on its, like that needs to happen in code. The programmer needs to account for it. And the moment something called, written statement is executed from the interrupt handler, what the CPU does is the CPU understands that, hey, I need to go ahead and kind of take the saved 8 registers and load them back into the CPU. And then our program counter value is loaded back and our CPU returns back to the process it was executed. Now, this must have been super duper heavy. We still haven't talked about how the new program counter value is inferred. And that brings us to the idea of vector table. And if the content that I have shared so far was heavy, I kind of encourage you to go back, revisit it, and very slowly kind of listen to it once again, because this is super, super key. Okay, so the vector table is the place from where it will infer what program counter value needs to be set. So we somewhere mentioned interrupt 25, that was like the interrupt we were working with. And again, all of this discussion we are having to understand the boot process. Um, so there is something called a vector table. And the idea is that vector table is list of an array, so to speak, of addresses which are essentially listing down that if an X interrupt happens, what memory location should be loaded in the program counter. So it's simply like a list of addresses, so to speak, from where to start fetching instructions. So each instruction or each array entry here is at a 4-byte boundary, and this is like C, then so on and so forth, +4. So what will happen is the 25th location starting from, like, including 4. So 4 is for the first exception or interrupt, 8 is for the second one, so on and so forth. So on the 25th location here, there would be a number A, B, C, D, let's say, hex A, B, C, D. So when the 25th interrupt happens, the CPU automatically takes 8 registers, saves them on the stack, and then loads the program counter with hex A, B, C, D, and then starts to fetch instructions from there. And this goes on until it sees the instruction called return, and return LR or return something like that. And once it sees that return instruction, it essentially says, oh, okay, now I must return back to doing my old job. And so that means restore back the PC value and restore back the other 7 registers and then move on from there. So the idea of vector table is like super, super important, and I'll kind of show you the details of this in a while. So now the thing is, why did we talk about all of this? And the answer to that is the reset. Um, the reset is one of the exceptions. So when the CPU starts off, it starts off as a reset exception. And so what will happen then is, well, reset happens to be the first exception. So um, this is kind of the memory, or this, whatever number happens to be here, it will load that straight into program counter. And the CPU will just start off by fetching instructions from that location. And this is super important to us because when we are writing our code in assembly, we are going to control what is the first instruction the CPU executes. Well, now you might ask, what is at this location, the 0th location? Why not go and pick, by the way, this is not 0th location, this is 0th offset from this vector table starting point. And in most cases, this vector table starts at the 0th address or the start of your code memory. That is typically where the vector table is. And the idea is, why not start from the 0th location? Why not take whatever number is in the 0th location and load it in the program counter? And the reason to that is, once we ask the question, who loads the stack pointer? The answer is that the stack pointer lives on the 0th location. So when the CPU boots up, it loads two registers automatically. One of them is stack pointer, which is loaded with whatever it is at the 0th address or the 0th offset of the vector table. And on the 4th offset, whatever number happens to be, that is treated as the memory location from where instructions are to be fetched. So then, simplifying, the boot process is, load stack pointer and program counter from 0th and 4th offset of the vector table. And once this is done, the CPU starts to fetch the instructions that the program counter is pointing at, right? And this is kind of, very neatly explained. The vector table essentially is neatly explained in the document, to which we'll come to in the next video.